In section 5.3, we're going to put together all the little pieces that we used in section 2 and go ahead and make an entire graph. So the first thing we're going to start out doing is factoring the numerator and denominator. From here, we're going to list the domain. And the way that we list the domain is we set the denominator equal to 0, and that's going to give us restrictions. Those restrictions might be wholes or vertical asymptotes, and we'll see how to tell the difference here in a moment. So let's flip to the next page and start looking at this function right here. So our first step is going to be factoring. So we'll have f of x equals, the numerator has a GCF of x, so it'll be x times x minus 4, and the denominator is going to factor to x minus 4 times x minus 3. So at this point, we're going to find the domain. So we will set the denominator equal to 0. So we get x minus 4 equals 0, x minus 3 equals 0. So x equals 4 and x equals 3 are our restrictions. So we would need to have a domain that excludes those two values. So it will go from negative infinity to 3, skip over 3, go 3 to 4, skip over 4, and go 4 to infinity. So that is our domain. Okay. Next, if any of the factors cancel, then there's going to be a hole in the graph. So when you have factors that cancel, there will be a hole in the graph. We need to exclude that value from the domain, which we already have because we did that in step 1. And then we're going to need to find the ordered pair of the hole. This is a step that often gets overlooked, and I'm going to show you how to do. Actually, I'm going to write how to do that here. So find the ordered pair of the hole, and we're going to do that by subbing the x value into the simplified function. Okay, so let's practice because our function actually has a factor that we can cancel out. So our step 2 is holes. And we found that by canceling out x minus 4. So we go x minus 4 equals 0. So we have a hole at x equals 4. Then we have a new function. Our simplified function is x over x minus 3. This is the function that we're going to work with from here on out. And we're going to use this function to find the ordered pair of the hole by plugging 4 in for the x value. So f of 4 would equal 4 over 4 minus 3, which is, oh goodness, 4 over 1. So our hole in this graph is at 4, 4. That's just coincidental. That's not always going to happen that it's the same x and y value. Okay. Next thing, intercepts. So our intercepts are going to include x-intercepts and y-intercepts. So for the x-intercepts, remember that they need to be in the format a number, comma, 0, and the way that we find them is by setting the numerator equal to 0. So we have x-intercepts that we will set the numerator equal to 0 for, and then y-intercepts are in the form 0 number. And to find the y-intercept, we're going to plug in 0 for x. If you have a multiplicity on your x-intercept, remember that that tells you if your graph bounces or crosses through. So multiplicity applies Did I spell that right? Yes. Multiplicity applies to those x-intercepts. Will the function cross or touch? Okay. Remember, if it's an even multiplicity, it's going to just touch the x-axis. If it's an odd multiplicity, it will cross through. Okay, so let's look at our example. Intercepts. So for the x-intercepts, we set the numerator equal to 0. Our numerator is x, so we go x equals 0. So our x-intercept is going to be 0, 0. To find your y-intercept, we're going to find f of 0. So that will be 0 over 0 minus 3, which is 0. So this one only has one intercept. The x and y intercept is the same value. Next, vertical asymptote. So the vertical asymptote also comes from the denominator after you cancel it. So vertical asymptotes have to be in that form, x equals 0. We find them by setting the denominator equal to 0, and that's after you cancel any wholes. These numbers need to be excluded from the domain, which we already took care of if we did that in step 1. Once you find your vertical asymptotes, remember that we need to use limits to, I need the word determine. So to determine if the graph goes toward positive infinity or negative infinity on the left and right side of the vertical asymptote. Okay. So we'll practice that using limits to determine if the graph goes towards positive or negative infinity on the left and right side of the vertical asymptote. So on our function, vertical asymptote, we're going to set the denominator equal to 0 and then use limits. Okay. So we've got the denominator on our new function is x minus 3. So x equals 3 is our vertical asymptote, which means that it is a vertical line, x equals 3. And then we need to determine what happens on the left and right-hand side of 3. So we had done that by doing the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. So we need to use our new function here, x over x minus 3. And when we had done this previously, we had chosen a value that was just slightly smaller on the left side and slightly bigger on the right side. So on the left side of 3, I might choose 2.99. So I'm going to plug in 2.99 for both of my x spots there, for both of my inputs. And I don't need to know the number that's going to come out. I just need to know if it's positive or negative. So this is going to be 2.99 is obviously positive. 2.99 minus 3 is negative. So this is going to be negative infinity. So what that tells me is on the left side of x equals 3, my graph is going to be headed towards negative infinity. Let's check the right side. The limit as x approaches 3 from the right side. So we're going to plug in a number slightly bigger than 3. It's like 3.01. So that will be, let's see, 3.01 is positive. 3.01 minus 3 is also positive. So this side heads towards positive infinity. So we are headed up on that side. Okay, what is next? Horizontal and oblique asymptotes. Okay, so horizontal and oblique asymptotes, we are going to use the original equation. Remember that n is the degree of the numerator, m is the degree of the denominator. So for our horizontal and oblique asymptotes, we're going to be comparing the degrees of our numerator and denominator. And I quit that word halfway through. So here are our guidelines. We practiced it towards the end of section 2. Let's look and see what we got going on here. So 5. Horizontal asymptote, oblique asymptote. So in our original function, the degree of the numerator is 2, and the degree of the denominator is also 2. Since those are equal, that gives me the horizontal asymptote is y equals the ratio of leading coefficients. So we're going to have a horizontal asymptote at y equals, the leading coefficient of the numerator is a 1. The leading coefficient of the denominator is also 1. So we will have a horizontal asymptote at y equals 1. Then we have oh shoot, I want to talk about this. So I had asked the question during section 2, or I had made the statement, I guess, that a function can cross a horizontal or oblique asymptote. So the way that we check that is to solve the equation where we set our function equal to the oblique asymptote to see if the graph intersects the oblique asymptote. Most of the time it doesn't, but it can. So if you were asked, does the graph cross its oblique asymptote, that would be how you do it. And you could do that for horizontal asymptotes as well. So let's see. Oh, shoot. What's next on here? Sign change chart. So with a rational function, the graph can only cross the x-axis at a certain number of locations. Like, it's allowed to cross the x-axis where there is an x-intercept, like all functions are. It's also allowed to cross, it's not really crossing, but it's allowed to be below the x-axis, then at a vertical asymptote on the next side of it, it can be above. So we need to check crossing spots using x-intercepts and vertical asymptotes, and I left out and holes to determine where the graph is positive, which would be above the axis, and negative, which would be below the axis. So we're going to do that by setting up a test chart. I know those are your favorite things. And we're going to plug in values in each of the sections to see if our input is or output is positive or negative. So you want to plug in values from each section to see if y is positive or negative. So positive is above the axis, negative is below the axis. That's going to help us draw our graph, so we'll know where we should be putting each section. These graphs are going to be divided into sections based on how many vertical asymptotes we have. So let's check our test chart in our problem here. Okay. So 6. We need to know we have a sine chart. Sine chart. So we've got the x-intercepts, vertical asymptotes, and holes. So x-intercept, vertical asymptote, holes. Our x-intercept was at 0, 0, so x equals 0. Vertical asymptote, x equals 3. And we had a hole at x equals 4. So those are really the only 3 values we need on our sine chart. 0, 3, 4. And then we need to pick a number somewhere in between negative infinity and 0. So like it really makes no difference. Negative 5, I don't know. I just kind of chose a number. And we want to plug this into the simplified function, which was x over x minus 3. So we got negative 5 over negative 5 minus 3, which is negative 5 over negative 8. Now, I would normally say it doesn't matter if we get the value or not, but in this case, because we just really need to know the sign, if it's positive or negative, but in this case, if we go ahead and compute that value of negative 5 divided by negative 8 and get 0.625, that's going to be an extra ordered pair that we can put on our graph. So negative 5.625, we can actually graph that as an ordered pair. But what that tells me is, since this y value is positive, my graph is going to be above the x-axis in this whole section. Let's see what happens between 0 and 3. So we'll go with x equals 1. So y would equal 1 over 1 minus 3. So that is 1 over negative 2. So our ordered pair would be 1 and then negative 0.5. Nice. Since that y value is negative, my graph is going to be below the x-axis in the section between 0 and 3. See what happens between 3 and 4. So x equals 3.5. Not ideal, but we have a calculator, so it's fine. So y would be 3.5 over 3.5 minus 3. So 3.5 over 0.5, which is 7 actually. So 3.5 comma 7. Since that's positive, my graph is again above the x-axis. And then between 4 and infinity, so maybe 5. So y would be 5 over 5 minus 3, which is 5 divided by 2. So that ordered pair would be 5, 2.5, which keeps my graph above the x-axis. So then once I have all of those parts completed, I have 6 parts, and then the 7th part is graphing. I think they kind of refer to that sometimes in their instructions, like use the 6-step process or use the 8 steps given on whatever. This is what they're talking about, is going through all of these steps. So all the things we're going to graph on there. I need a highlighter. How do I not have what I need? Like super handy. Okay, pause. Okay, found a highlighter. So we're going to put on the graph holes as open circles, x and y intercepts as points, horizontal and oblique asymptotes as dashed lines, remembering that the graph may touch or cross them, but they determine end behavior. And vertical asymptotes, they go on the graph as dashed lines. Your graph is not allowed to touch or cross, and we are going to use limits on each side. Okay. So going through our information here. The holes. that is going to go on as an open circle. So 4, 4 is going to go on my graph as an open circle. Let's find that on our graph paper. Good gravy. I don't even have axes drawn on here. Let's do that. There we go. So 4, 4 is going to be an open circle. 1, 2, 3, 4. 1, 2, 3, 4. Right there. What is next? X and Y intercepts. Well, this one only has the one intercept, and it goes on as a solid dot. So 0, 0 is going to be a solid dot. What's next to go on? Horizontal and oblique asymptotes and vertical asymptotes. So our horizontal oblique asymptote, this guy goes on as a dashed line. So at y equals 1, we will have a horizontal line that is dashed. Now keep in mind that our graph is definitely allowed to cross that, but it doesn't always. What's next? Oh, the vertical asymptote. Let's get that guy going. So we're going to graph x equals 3 as a dashed line on our graph. And then we also need to remember that on the right and left-hand side of x equals 3, our graph is headed towards negative infinity on the left and positive infinity on the right. So what I will usually do is get my asymptote going on there. And I usually just put an arrow on the right side. So mine was up on the right and down on the left. So I put an arrow on that side and an arrow on this side. So that's just going to remind me that I need to connect to those arrows when I draw my graph. Okay. Then I did not list this, but I would say that you should also include those extra ordered pairs that we graphed. There it is. So include the extra ordered pairs and above below. Info. Okay. So let's go. So I've got that my graph should be above the x-axis between negative infinity and 0. So from negative infinity to 0, my graph is going to be above the x-axis. And then what? Did I have a mistake there? No, I did not. We're good. And then it's going to cross through the x-axis here. I lost track of myself for a moment. And then it's going to be below the x-axis until we get to 3. So above the x-axis in this section until we get to 0, it crosses through right there, and then it's below the x-axis after that. So we could check to see some additional ordered pairs on our graph, but knowing that my graph is going to be above all through this section, then it's going to cross through, and then it's going to be below. That gives me a pretty good idea of what this graph is going to look like. Even if I don't know for sure if my graph crosses or touches the horizontal asymptote, I do know that it's going to run along that asymptote. So I can just kind of connect my dots here and add in my additional ordered pairs that I had. What were those? So I know that we were above, below. I can add in these ordered pairs that are extra. So I can put those guys in, negative 0.5, 0.625, so that's about here. 1, negative 0.5, right there. What do we have? 3.57, 3.5, 1, 2, 3, 4, 5, 6, 7. And then 5, 2.5. Then I know that my graph is above all the way from 3 to infinity. So we are above forever after that. Let's see what we can do to make this graph happen. I know I need to go through these ordered pairs and hit this arrow down here. Oh, haha, you guys. I'm sure you all were like, why did you put that ordered pair there, Miller? It's negative 5.625. 1, 2, 3, 4, 5.625. There we go. I was like, those points are too close together. I'm sure you're doing it right. Just keep doing it right. So I'm going to have to hit these ordered pairs, run along this asymptote, go below the axis, run along this asymptote down to that arrow. So that's the graph we're going to get. By the way, when you take this test, you're not going to be using a graphing calculator because your calculator will actually graph this for you. And I want you to be able to graph it with the information that we are finding. Then on this side of the vertical asymptote, I know I need to go through these ordered pairs, run along this horizontal asymptote up to this vertical asymptote arrow here. Now I can figure out if my function ever crosses the horizontal asymptote. So let's look at that now that I have it drawn and see if I did okay. So will the function intersect the horizontal or oblique asymptote? So what we do for that is we set the function equal to the asymptote and see if it solves. So our function was x over x minus 3. Our asymptote was y equals 1. So we're going to solve that by multiplying both sides by x minus 3. So that gives us x equals x minus 3. If we subtract x from both sides, we get 0 equals negative 3. Since that is not true, we didn't get an x value, we got something that's false, then the answer to that is no. The graph will not intersect the horizontal asymptote. So we're going to come back in a little while, or whenever you feel up to it, and we're going to go through this second example together. But for now, I think this is a good time to end.